Good morning, ma'am. This is 𝙎𝙀𝙉𝙍𝘼 from CSNB. Now I am here to explain my assignment topic: optimal binary tree, optimal binary search tree by dynamic programming. Introduction to optimal binary search tree. Optimal binary search tree are data structures that minimize search time. They are practically useful when the access probabilities of keys are unknown. The goal is to construct a tree that reduces the average search cost based on these probabilities. Basics of binary search tree. Binary search tree is a tree structure. There each node has a most two children. The left child value is less than its parent's value, while the right child is greater. This property allows for efficient searching, insertion, and deletion operations. Importance of optimal binary search. An unbalanced binary search tree can lead to increased search times. The performance can degrade into linear time to the worst case, particularly for sorted. The optimal tree minimizes the expected search time based on key access frequencies. Problem definition. Given a set of keys and their respective access probabilities, the goal is to construct an optimal binary search tree. The tree should minimize the total expected search cost across all keys. This search is cost computed by multiplying the probability of access by the depth node. Dynamic programming approach. Dynamic programming is used to break down the problem into similar subproblems. We create a table that stores solutions for smaller trees to build larger ones. This approach significantly reduces the computational complexity compared to naive methods. Cost calculation. The cost of binary search tree is defined as the sum of products of probabilities and depths. The depth of each node is determined by its position in the tree. The objective to minimize this total cost through the optimal tree structure. Key concept. The keys are represented as distinct nodes in binary search tree. Access probabilities are associated with each key based on historical usage data. The concept of subtrees is crucial for calculating in a dynamic programming context. Dynamic programming table construction. A 2D table is created where each entry represents the optimal cost of a subtree. The table is filled in bottom-up manner, starting from smaller subtrees to larger ones. Each entry is calculated based on the previous entries and access probabilities. Cursive formulation. The cost of subtree can be expressed recursively based on its children. The formula incorporates the cost of left and right subtrees and the root node steps. This recursive deletion is fundamental for filling in dynamic programming table. Example of optimal binary search tree construction. Consider a set of keys with unknown access frequencies. The dynamic programming approach iteratively calculates cost of for all subtrees combination. The final table provides the optimal structure for the entire set of keys. Roots. The choice of roots is crucial in minimizing the overall cost. For every possible root, the cost of left and right subtrees are evaluated. The route that yields the minimum total cost for the subtree is selected. Complexity analysis. The time complexity of the dynamic program approach is O(n)(3). This arises from the need to consider all pairs of keys for subtree combinations. Subspace complexity O(n)(2) due to the storage of the dynamic programming table. Applications of optimal binary search tree. Optimal binary search trees are extensively used in database indexing and retrieval systems. They can enhance performance in applications where certain keys are accessed more frequently. This makes them valuable in areas like search engines and data retrieval systems. Limitations and challenges. The primary limitation is need for accurate probability estimates for keys. Inaccurate probabilities can lead to suboptimal tree structures. Additionally, the computational overhead may be a concern for very large data sets. Conclusion: optimal binary search trees are significantly improved search efficiency for key access. Dynamic programming provides a systematic approach to constructing these trees. Understanding optimal binary search trees is essential for optimizing data structures in computer science. Thank you, ma'am, for giving this. Thank you, ma'am, for giving this topic to me and to understand and the topic more efficiently and to tell you the topic very nicely. Thank you, ma'am, for giving this opportunity.